Welcome to On Chemistry. We are seeing organic chemistry concepts. In this video, we will see Favorskii rearrangement. It is a rearrangement reaction with carbon skeleton change. We will help you to understand with 28 fully solved problems. Stay tuned. What is inside this video? First, we will see what is Favorskii rearrangement and mechanism behind rearrangement reaction. Then basics and enolate formation, steric effect, and what will happen in the cyclic system. More importantly, we will help you to understand Favorskii rearrangement with 28 fully solved examples. Those questions are from various examinations I compiled and given to you. First, let us see what is Favorskii rearrangement. It is a carbon skeletal change reaction. Normally, it is occurred with carbonyl group and one leaving group and the carbon with acidic proton and the alpha hydrogen. So, if you use the base, rearrangement happen, you end up with ester. So, you start from alpha substituted ketone to the ester. Here base can be anything. Here I given sodium hydroxide or ethoxide. Leaving group can be chlorine, bromine, tosylate, mesylate and triflate. Light also sometimes can be a catalyst if there is a good leaving group. We will see the mechanism. Here why you should have alpha hydrogen mean the intermediate is cyclopropanone. It is only possible by generating the nucleophile. So first step will be removal of proton. If the compound has many alpha proton, regioselectivity will be followed. We will see shortly. First we will see the mechanism. So proton abstracted mean you have nucleophile. So negative charge is the nucleophile. It can attack the chlorine. It forms cyclopropanone. Then sodium methoxide. Sodium methoxide add to the carbonyl through nucleophilic addition. So new CC bond. Then you have the charge in the system. Charge has to be quenched. So cyclopropane ring also has to be open because of its high strength. So ring is open. The ring open in such a way that to form a stable anion. So anion has to be quenched. H plus react. You end up with final product. If you look at it, you start from ketone, end up with ester there. The whole mechanism is simple. Nucleophile generation, cyclopropanone formation, ring opening. So all steps will be easy if you understand the basics. Then the regioselectivity. There can be two types of regioselectivity. We will see one by one. Suppose you have two alpha hydrogen mean which will be removed. Here I shown the condition 2 alpha hydrogen A and B. So both you can remove form the nucleophile but A is the major. Why? Because it form more stable enolate which is more substituted enolate. More substituted enolate is stable because of its thermodynamic stability. Why we are not talking nucleophile mean the negative charge want to stay on the oxygen not on the carbon. So enolate formation dictated there. So more stable enolate will form. The first regioselectivity you should learn here is more substituted enolate will form. We will see the second regioselectivity in Favorskii rearrangement. Intermediate is cyclopropanone. The cyclopropanone ring has to be opened. Which side it will open? It can open either way. Here I shown A and B. If B side breaks mean you form the more unstable anion. So only A side break happen. It form primary anion. If you look at the anion stability, primary is more stable than secondary. So A break is major, B break is minor. So the regioselectivity you should learn here is the cyclopropanone ring open to form a stable anion. Then the next basic, the anion stabilizing group. Since the ring opening form anion, you should know the anion stability. Normally low charge or no charge is stable. So the charge decreasing species stabilize the anion. So electron withdrawing group stabilize the anion. The withdrawing group can be a electronegative group or low hybridization or positive charge, nitro and cyano. On the contrary, electron donating group destabilize the anion. It makes the anion unstable. It don't form. Conjugation also stabilize the anion. So you should know the anion stability. Among the anion stability, aromatic anion is more stable. It forms predominantly. It's a big topic. If you are interested, go and study yourself. Then the interesting fact, the ring contraction. If the Favorskii rearrangement happen in the ring mean one size reduction happen, 6-member ring will become 7-member ring, but carbon atoms are same, but ring only contracted. One carbon go out of the ring, form a ester, so ring contraction. So if you start with 6-member, end up with 5-member. If you start with 7-member, end up with 6-member. One carbon less in the ring. Then the important basics, you can control the product by controlling the base. If you use sodium hydroxide, end product is acid. If you use sodium methoxide, end product is ester. If you use sodamide, end product is amide. So the concept you have to learn here is by controlling the base, you can control the final product in Favorskii rearrangement. Then we are getting into the important category, solved examples. We solved almost 28 examples fully with mechanism. To help you to understand the concepts better, you may wonder why so many, because problems are best way to learn. It will give different perspective and complete understanding. Let us see the first example. Here you have ketone. One side you have alpha carbon with chlorine, another side alpha carbon with phenyl. Basically it's a benzyl group. You are using sodium methoxide. You should find what will be the final product. Here by looking at the alpha haloketone, you might realize it's a Favorskii rearrangement. First step will be abstraction of proton. For that you have to redraw the molecule with hydrogen and phenyl. So if you redraw it, you have alpha hydrogen removal, form the nucleophile. You have nucleophile in the system. Chlorine is the good living group. So nucleophile attacks. You have new CC bond and cyclopropanone ring formation. Then methoxide attack. You have to open the ring. Which side ring will open? The anion stabilizing side ring open. Here benzene can stabilize the anion by the resonance. So ring open. You have the anion. Then anion is quenched by hydrogen. You end up with final product. The concept you have to learn here is in Favorskii rearrangement, always stable anion forms. Then the next example. Here you have bicyclic system. Bridged carbonyl is there. It's a ketone. Alpha position you have bromine, which is also a connected carbon or bridged carbon. You are using sodium methoxide. You should find what will be the final product. Here compound is bicyclic. Don't get confused. Stick with fundamental. We will go by the structure. Here you have alpha hydrogen atom and alpha halogen ketone. So chances of Favorskii rearrangement. You are using sodium methoxide. It is a base. Abstract the proton. You have the nucleophile. The nucleophile attacks the bromine. It forms cyclopropanone. Then O methoxide attacks. Ring has to be opened. So ring open. Both sides are same. So you can open either side. It's a symmetrical system. Then anion quenched by H plus. You end up with final product. If you redraw nicely, you end up with fused compound. So you start from bicyclic compound, end up with fused compound. The concept you have to learn here is in ring system, Favorskii rearrangement reduced the ring size, but in bicyclic system, it converted into the fused compound. Then the next example, here you have cyclohexanone, alkene you have, and you have methyl isopropene in the system. You are using bromine and sodium hydroxide. You should find what will be the final product. You will go by the basic instead of doing Favorskii rearrangement. First step, you are using the bromine. You have alkene in the system. Alkene undergo bromine addition. You have 1,2-dibromide. Then you have alpha haloketone. The chances of Favorskii rearrangement. So first step will be abstraction of proton. Here you have alpha hydrogen. It abstracted by sodium hydroxide. You have the anion. The anion is the nucleophile. It attacks the alpha bromine. It forms cyclopropanone. Then sodium hydroxide attacks the carbonyl. The cyclic ring open. It open on the bromine side to quench the charges. So ring open, bromine eliminates. You end up with alkene. Here bromine provide different quenching mechanism because it is a good leaving group. So bromine eliminates. So you end up with final 5-member product. Ring is contracted. If you redraw nicely, you can clearly see 6-member ring will become 5-member ring. The concept you outline here is in Favorskii rearrangement, ring contraction happened. Then the next question. Here you have cubane-like system, one rigid carbonyl. You are having alpha bromine. You are using sodium hydroxide as the reagent. You should find what will be the final product. The system is big system, but we stick with fundamental alpha haloketone with alpha hydrogen. You are using the base, so Favorskii rearrangement. Base abstract the proton. You have the anion there. Anion is the good nucleophile. It attacks the bromine. You have cyclopropanone. The cyclopropanone is strengthful. So NaOH, OH minus attacks. You have the ring opening. Ring opening leads to the anion in the system. It quenched by H plus. You start from 5-member in one phase, end up with 4-member. Basically, it's a ring contraction in the cubane system. Here, stability of the cubane can promote the product. The concept you outline here is even in bicyclic system, you will end up with one less ring size. Then the next example, here you have toluene, side chain you have ketone with alpha bromine and alpha methyl. You are using sodium methoxide, acid hydrolysis in reflex condition. You are using the polyphosphoric acid. You should find what will be the final product. Here you have alpha haloketone and alpha hydrogen. You are using the base. So Favorskii rearrangement. So first step will be abstraction of proton. You have the anion. Anion is a nucleophile. It attacks the halogen. You have cyclopropanone. The cyclopropanone is the strainful ring. So sodium methoxide attack means it will easily open. So the ring open to form a stable anion. It open in the side of the benzene ring. So anion formed on the benzene ring. It quenched. You have ester there. Then you are using acid in reflex condition means ester become acid. Then if you are using ester in acidic hydrolysis condition mean ester become carboxylic acid. Then the next reagent is polyphosphoric acid. It form acyl cation, attack the ring. You have alpha substitution. It's aromatic electrophilic substitution reaction. You end up with final cyclic product. The concept you outline here is always you should master the reagents along with Favorskii rearrangement. Then the next reaction, you have cyclohexanone. Second position you have chlorine. You are using sodium ethoxide and ethanol. You should find what will be the final product. Here you have alpha haloketone, alpha hydrogen also there. You are using sodium ethoxide. So chances of Favorskii rearrangement. Sodium ethoxide is the base. It abstracts the proton. It forms the anion. The anion is the nucleophile. It attacks the chlorine. Chlorine leaves. You end up with cyclopropanone. Cyclopropanone in the strainful system. So sodium ethoxide attacks, you end up with Ester there because ring open to reduce the strain. You have anion, then the anion quenched by the hydrogen. You end up with final product. You start from 6 member, end up with 5 member. The concept you outline here is in cyclic system, always ring contraction happen in the Favorskii rearrangement. Then the next question. Here you have ketone. 2 alpha position you have 2 bromine, 1 methyl and phenyl. You are using sodium methoxide and methanol. You should find what will be the final product. Here you have ketone, alpha hydrogen, bromine. So chances of Favorskii rearrangement. First step will be abstraction of proton. You form the anion. Anion is the nucleophile. It attacks. You have cyclopropanone. Then cyclopropanone ring attacked by sodium methoxide. You have to open the ring there. So anion has to be quenched. It quenched as carbonyl by the ring opening. Ring open by the elimination of bromine. It's an alternative quenching pathway. You end up with alpha, beta, unsaturated ester. So you start from ketone, end up with alpha, beta, unsaturated ester. This kind of product will be obtained when you have two leaving groups. Then the next example, here you have cyclohexane, tertiary butyl group is there, and you have ketone with CH2Cl. Both groups are above the plane. You are using the sodium methoxide. You should find what will be the final product. Here alpha halogen is there, alpha hydrogen is there. So chances of Favorskii rearrangement, the compound given with stereochemistry. So we redraw to the chair form because we have to find the influence of stereochemistry. So we draw in the chair form. So clearly with hydrogen and chlorine, you are using sodium methoxide. It is the base, abstract the proton. You form anion. The anion is the nucleophile. It can attack the CH2 carbon. Chlorine is the leaving group. It forms cyclohexanone. Cyclohexanone is the strainful ring. So it is again attacked by methoxide. Ring opening happen. Which side ring will open? Ring open to form stable anion. So ring open. Stable anion is methylene anion. Then H plus attacks. You end up with CH3. Since ring open with CH2 side, you have COOMe above the plane. So we draw with stereochemistry. So if you redraw nicely in the planar form, COOMe and tertiary butyl above the group, methyl below the plane. The concept you outline here in cyclohexyl system, better you redraw with stereochemistry and find the product. Then the next example, here you have bicyclic compound with ketone, alpha bromine, bridged nitrogen with acid group. You are using the sodium hydroxide. You should find what will be the final product. Here structure may be big. We will stick with the fundamentals. Here we have carbonyl group. One is ketone, one is acid. But alpha halogen with ketone and hydrogen. So chances of Favorskii rearrangement. So we do the reaction in the carbonyl. Sodium hydroxide you are using, which abstract the acidic proton, that is alpha proton. It form anion. Anion is the nucleophile. So it attacks the carbon, bromine leaves, you have cyclopropanone. Cyclopropanone is the strainful system. It is again attacked by OH minus, ring open, you form anion. Then the anion quenched by H plus. You end up with final product. Since bicyclic system is the cyclic system, you end up with one carbon less, it become acid there. The concept you outline here is even in bicyclic system, ring contraction happen in the Favorskii rearrangement. Then the next example, you have cyclohexanone, alpha position you have chlorine, you are using sodium ethoxide and ethyl alcohol. You should find what will be the final product. Here you have alpha chlorine, alpha halogen, carbonate, base you are using. So chances of Favorskii rearrangement. Sodium ethoxide is the base. It abstracts the proton. You form the anion. The anion is the nucleophile. It attacks the chlorine. You have cyclopropanone. It is the strainful system. It is three-member ring strainful system. So it again attacked by sodium ethoxide. Ring has to open. There are two possibilities, but system is symmetrical mean both side possibilities. Since the carbon is labeled, we have to write both the compound with stereochemistry. If you find it, you have ring contraction with 5-member ring with ester. If you read on nicely, you can see two different possibilities by the labeled carbon. Chemically same, but technically we differentiate with isotopes. The concept you outline here is if you use isotopic study, you end up with different isomers in Favorskii rearrangement. Then the next example, here you have ketone, one side with cyclohexane, another side with chlorine attached with cyclohexane. You are using the base sodium hydroxide. You should find what will be the final compound. Here ketone is there, alpha halogen is there. The starting material contain carbonyl, alpha hydrogen, alpha chlorine. So chances of Favorskii rearrangement, you are using the base. Base subtract the proton. You form the anion. The anion is the nucleophile. It attacks the chlorine. It forms cyclopropanone. Cyclopropanone is the strainful ring. So OH minus attack through nucleophilic addition. Ring open. You form the anion. Ring open to form stable anion. Secondary anion. So it is stable. It is quenched by H plus. The concept you outline here is you always go with basics to find the final product in Favorskii rearrangement. Then the next question. Here you have ketone. Alpha position you have bromine. Another side you have bromine with isopropyl group. You are using sodium methoxide and methanol. You should find what will be the final product. Here you have carbonyl and you are using the base alpha halogen. So chances of Favorskii rearrangement. First step will be the abstraction of proton. The abstraction leads to the anion formation. Anion is the good nucleophile. It attacks the bromine which is the leaving group. It forms cyclopropanone. The cyclopropanone is strainful ring. So methoxide attacks. You have nucleophilic addition. The addition creates the charge. Charge has to be quenched as well as strain has to be relieved. So O minus become carbonyl with the ring opening, form the stable anion. Here charge quenched in the different way, while the ring open with less stable anion because the quenching pathway by bromine elimination. So anion attacks the bromine, it form alkene. The driving force is conjugation. So final product, if you look at it, it's alpha, beta and saturated ester. You end up with final unexpected product. The whole reaction involves different pathway of quenching anion. This is due to two leaving group in the starting material. Then the next question. Here you have cyclohexanone. Second position you have alkene which has side chain bromine. You are using sodium methoxide. You should find what will be the final product. The starting material has alpha hydrogen and ketone. Only twist is bromine is on side chain, but it is in conjugation with alkene. So it's a kind of variation in Favorskii rearrangement. Same pathway follows with SN2 prime mechanism. First step will be you are using the base. Base subtract the proton. It form anion. Anion is the nucleophile. It can attack the alkene carbon to promote the SN2 prime mechanism. So anion attack, charge migrate. You have alkene there. Then methoxide attacks the cyclopropanone ring. Ring try to open. It open to form stable anion. So it open, form the anion. It quenched by H plus. So if you redraw nicely, you clearly see ring contraction happen with 5-member ring with alkene and ester. The concept you outline here is reaction always move towards good leaving group. Here it is in conjugation with ketone. So it happened. So modified version of Favorskii rearrangement happened. Then the next example, here you have cyclohexanone, alpha position you have bromine and other alpha position you have 2 deuterium. You are using aqueous NaOH. You should find what will be the final product. Here you have deuterium instead of hydrogen, which is the high molecular weight heavy hydrogen. You have alpha bromine carbonyl. So chances of Favorskii rearrangement. First step will be abstraction of proton. Here it is deuterium. The abstraction happened. You have the anion. Then the anion attacks the bromine carbon. The attack happened. You have cyclopropanone. Here ring can open either side, but deuterium may create the confusion. Deuterium cannot influence the electron density. So both the possibilities are there. So 50-50 chance. Mixture of products obtained. The concept you outline here is always you should master the fundamental. Deuterium is like hydrogen, cannot mobilize the electron density. Then the next example, here you have ketone. One side you have methylene bromide, another side you have bromine, phenyl and methyl. You are using the base in methanol. You should find what will be the final product. Here many possibilities. Let us start with basics. The carbonyl has alpha hydrogen, alpha bromine. So chances of Favorskii rearrangement. First step you are using the base. Base subtract the proton. It form anion. The anion is the nucleophile. It attacks the bromine carbon, form cyclopropanone. Then sodium methoxide is there. Sodium methoxide attacks the carbonyl. Nucleophilic addition happen. You have O minus. Charge in the system is unstable. So ring try to open itself by the carbonyl formation. Ring open on phenyl side because of stability with phenyl system. So phenyl methyl hold the anion. Then the anion quenched by alkene formation. Here alkene formation driven by the conjugation because alkene and carbonyl conjugate to each other. So final product is alpha, beta unsaturated ester. The concept you outline here is whenever you have two alpha halogen in the system, you end up with alpha, beta unsaturated system. Then the next question. Here you have ketone, both sides cyclohexyl group. You are using sodium hydroxide and bromine. You should find what will be the final product. Here ketone is there, both sides cyclohexyl. Starting material is sodium hydroxide. So the first step will be abstraction of acidic proton, form the anion. Then the anion attacks the bromine. you form new carbon halogen bond. The halogen is alpha halogen, so chances of Favorskii rearrangement. Again, the alpha proton abstraction. Alpha proton abstraction leads to the nucleophile anion. Anion attacks the bromine carbon. It forms cyclopropanone. It is the strainful system. So sodium hydroxide again attacks. You have ring opening because charge has to be quenched. So anion travels to the carbonyl. Ring open. You end up with anion. Hydrogen abstraction. Finally, acid is there. Here start with ketone, end up with acid, but both cyclohexyls are connected. The concept you outline here is strain can assist the final product. The strain of cyclopropanone assists the reaction. Then the next example. Here you have cyclohexanone, bromine and acetic acid you are using. Sodium methoxide is the second reagent. You should find what will be the final product. Here ketone is there. You are using the base. Base subtract the acidic proton. Acidic proton is alpha hydrogen. So it form nucleophile, that is anion. Anion attacks the bromine. It form alpha halogen. Alpha halogen and carbonyl. So chances of Favorskii rearrangement. So same base you are using. Base subtract the acidic hydrogen. It form anion, which is the nucleophile. Anion attack the good leaving group. Bromine elimination. It forms cyclopropanone. Cyclopropanone is strainful system. So methoxide attacks through the nucleophilic addition. You form anion in the oxygen. It has to be quenched. It quenched by carbonyl formation and ring contraction. So you start with 6-member ring, end up with 5-member ring. The concept you outline here is, here starting material is twisted. So you should master basic organic chemistry to master the Favorskii rearrangement. Then the next example, you have ketone, alpha position you have chlorine and benzyl. You are using the methoxide. You should find what will be the final product. Here carbonyl is there, alpha halogen is there, alpha hydrogen also there. So chances of Favorskii rearrangement. You are in the base, base subtract the proton, form the anion. The anion is stable and nucleophile. So it attacks the chlorine carbon. Chlorine is the leaving group, form the cyclopropanone. The strain in the system has to be relieved. So methoxide attacks, you form new CO bond. The addition leads to the anion. Anion has to be quenched. So what really happened? Anion forms the carbonyl. Ring open to the phenyl side. The phenyl anion is stable. It quenched by H plus, end up with final product. So you start from ketone, end up with ester through the carbon skeleton change. The concept you outline here is ring strain assists the reaction. Here cyclopropanone form, highly strainful, assists the final product formation. Then the next question, here you have cyclohexanone, alpha position halogen. Alpha position also has the isopropyl group with bromine, and in the fifth position you have methyl group above the plane. You are using sodium methoxide. You should find what will be the final product. Here many functional group. We only focus on our interest, that is Favorskii rearrangement. Alpha bromine is the carbonyl. So Favorskii rearrangement possible. First step will be abstraction of proton. You form anion. The anion is the good nucleophile. Inside good leaving group is there. Anion attacks. It forms cyclopropanone. Cyclopropanone is the strainful system. So methoxide attack through nucleophilic addition. It open the ring. Ring can open either way. but bromine side is better because it has internal quenching group which is bromine. So anion open on bromine side, then anion quenched by bromine elimination by alkene formation. So if you redraw nicely, you can clearly see you end up with 5 member, same configuration of methyl group, only quenching pathway is different. The concept you outline here is in Favorskii rearrangement, stereochemistry won't play the major role. Then the next question. Here you have cycloheptanone, 7 member ring. Alpha position you have chlorine. You are using the sodium hydroxide. You should find what will be the final product. Here ketone is there, alpha hydrogen is there, halogen is there. So the chances of Favorskii rearrangement. Here base remove the alpha hydrogen, form the anion. The anion is the nucleophile. You have leaving group inside the system which is chlorine. So anion attack chlorine carbon, form cyclopropanone. Cyclopropanone is the strainful ring. So it attacked by OH through nucleophilic addition as it forms ring open. You have the anion. Since the system is symmetrical, both side anion is stable. So we draw with one side, then the anion quenched by H plus. You end up with final product. If you redraw nicely, you end up with 6 member. So you start from 7 member, end up with 6 member. The concept you outline here is in Favorskii rearrangement, ring contraction happen. Then the next example, here you have cyclobutanone, alpha position you have bromine, sodium hydroxide you are using, which contain deuterated hydrogen. You should find what will be the final product. The starting material is ketone. You have alpha hydrogen, alpha bromine, base you are using. So Favorskii rearrangement. Here deuterium given for the distraction. Same result you obtained with deuterium. Only hydrogen replaced with deuterium. First step will be base subtract the proton. You form nucleophile. A nucleophile is anion which attacks the bromine containing carbon. Bromine is the good leaving group. So anion attacks. You have cyclopropanone. You are going to most strainful system. But let us proceed with mechanism. The system is very strainful. So OD minus attack. It is like OH minus. It attacks, ring open, form the anion. Since the system is symmetrical, both products will be same. You end up with Ester there. Here ring contraction happened. Even though it formed very strained 3 member ring. The concept you outline here is deuterium cannot alter the electron density. You end up with same results like hydrogen. Then the next example. Here you have macrocyclic ring with carbonate. You are using the bromine and ether and sodium methoxide. You should find what will be the final product. Here bromine you are using. Two acidic proton will be readily replaced by the bromine. So bromine gives the possibility of Favorskii rearrangement because it is in alpha position. So we use sodium methoxide. It is the base. Base subtract the proton, form the anion. Anion is the nucleophile. It attacks the bromine. It forms cyclopropanone. It is the very strainful system. So it again attacked by methoxide through nucleophilic addition. It will open the ring. The ring open in such a way that quenching through bromine because bromine is internal quenching group. Anion quenched as alkene by bromine elimination. Here ring contraction happen with the macrocyclic. The ring is one carbon less than the starting material. The concept you outline here is if you have two alpha halogen, you end up with conjugated system. Then the next example. Here you have cyclohexanone. Alpha position you have chloride. In port position you have tertiary butyl. You are using sodium methoxide. You should find what will be the final product. Here cyclohexane is given. Better we redraw the molecule to identify any role of stereochemistry. So we redraw the molecule to the chair form with same configuration. Chlorine above the plane, tertiary butyl above the plane, and ketone in the system. You have alpha hydrogen, alpha chlorine, sodium methoxide. So Favorskii rearrangement. So first step will be abstraction of proton. Form the anion. Anion is the nucleophile which attacks the chlorine carbon. Why? Because chlorine is the good leaving group. Form the cyclopropanone. Cyclopropanone is the strainful system. So methoxide again attack. It open the ring. Ring can open either way because system is symmetrical. You form anion. Then the anion attacks the H plus. You end up with ester there. Here no stereochemistry is required because ring is puckered or you can say distorted. The concept you outlined here is in Favorskii rearrangement, most of the time stereochemistry don't play any role. Then the next question. Here you have beautiful ring system with ketone and bromine. You are using the sodium methoxide. You should find what will be the final product. Here the answer is same. Only thing is you should not confused with big ring system. Ring is big, but we stick with our own fundamental. Starting material has ketone, alpha hydrogen, alpha bromine. So Favorskii rearrangement. First step will be abstraction of proton. You form anion. Anion is the good nucleophile which attacks the bromine carbon because bromine is the good leaving group. Form the cyclopropanone. The cyclopropanone is the strainful system. It attacked by methoxide. It opened the ring, formed the anion. Then the anion quenched by H plus. You end up with ring contraction. The product has one less carbon with starting material because it forms ester with side chain. The concept you outline here is even in macrocyclic system, you end up with one carbon less. Ring contraction happen. Then the next example. Here you have cyclohexanone, ketone and halogen, tertiary butyl group. Both are above the plane. You are using sodium methoxide. You should find what will be the final product. Here you have alpha hydrogen, alpha halogen, carbonate and base you are using. So Favorskii rearrangement. So first step will be abstraction of proton. Proton abstraction happen. You have anion. Anion attacks the chlorine carbon because chlorine is the good leaving group. Anion attacks, you have cyclopropanone. Then cyclopropanone ring has to be open. Why? Because it is a strainful system. So methoxide attacks, nucleophilic addition happen which open the ring. Ring open in such a way that to form the stable anion because primary anion is more stable than tertiary. Primary anion formed, it quenched with H plus. So final product you have ester. The concept you outline here is stereochemistry sometimes given for distraction. You focus on fundamental, predict the final product. Then the next question. Here you have decline system. In connected carbon, you have alkyl and hydrogen trans to each other and you have ketone, alpha halogen in the system. You are using sodium methoxide. You should find what will be the final product. Here system may be different, but we focus on fundamentals. Here you have ketone, alpha halogen, alpha hydrogen, So Favorskii rearrangement, base you are using, base subtract the acidic proton, you form anion. Anion is the good nucleophile. It attacks the bromine carbon because bromine is the good leaving group. The attack leads to the cyclopropanone. You create the strain in the system. Then strain should be relieved. So methoxide attacks through nucleophilic addition, which form anion with the ring contraction. Anion quenched by H plus. You end up with final product. Here you start from decline, but ring size is reduced by one carbon because it formed ester in the side chain. So ring contraction happen even in the cyclic system. Then the next example, here you have ketone, one side alkyl group, another side dibromomethane. You are using sodium methoxide. You should find what will be the final product. Here we should focus on fundamentals. Starting material you have carbonyl, alpha hydrogen, alpha bromine. So chances of Favorskii rearrangement. So first step will be abstraction of proton, which leads to the nucleophile formation. The negative charge acts as a nucleophile, attacks the carbon with bromide because bromine is a good leaving group. The attack leads to the cyclopropanone ring formation. It is very strainful. It should be relieved. So methoxide attacks through nucleophilic addition, which open the ring. The ring open on carbon side, not the bromine side, because of better quenching pathway. Anion form in the carbon. Bromine is the good leaving group, so it form alkene. So you end up with alpha, beta, unsaturated ester. The concept you have to learn here is whenever you have dihalogen in the system, it provide alternative mechanism. End up with alpha, beta, unsaturated ester. Then the final example, the similar examples we seen but with bromine variation. Starting material is cyclohexanone. With alpha position you have bromine, sodium methoxide, methanol. You should find what will be the final product. The starting material has carbonyl, alpha hydrogen, alpha bromine. You are using the base. So chances of Favorskii rearrangement, base subtract the proton, you form the anion. Anion is the good nucleophile. It attacks the bromine carbon because bromine is the good leaving group. Anion attacks, you have cyclopropanone. It is the strainful ring. So methoxide again attacks. You have nucleophilic addition with O minus formation. The charge has to be quenched. The charge quenched with carbonyl formation and the anion. You end up with ester. If you look at clearly, you start from 6 member, end up with 5 member. The concept you have to learn here is in Favorskii rearrangement, always ring contraction happen. Let us summarize what we learned. In Favorskii rearrangement, you should have carbonyl, alpha hydrogen, alpha leaving group. If you use the base, you end up with ester with the carbon skeleton change. The final product is tunable, but fundamentally it is ester. Here you have two regioselectivity. First one is more substituted enolate will form because it is thermodynamically stable. Second one is ring open always to form a stable anion. Then leaving group better to be the anti-periplanar position. It will help the carbon-carbon bond formation as well as assist the bromine elimination. The last and important thing is ring contraction always happen in the cyclic system.